Well, hey there, everyone. Today we're going to be looking at the Chapter 11 practice test. Questions 1 through 5, starting with number 1. Find the slope of the polar curve r equals 4 minus 8 sine theta at theta equals 0. Our first realization here is that in order to get the slope, we need a dy dx. And when you say see polar curve, really you should be thinking of this is just a parametric curve with some very specific parameterizations. So for a parametric curve, any plane parametric curve, we have the slope is equal to dy dt over dx dt. Since this is a polar curve, the parameter that we're going to use is not going to be t, it's going to be theta instead. Next, we have that the y-coordinate is actually equal to r sine theta. So we're going to take the derivative of r sine theta with respect to theta. And then we're going to put that on top of d theta for the x-coordinate. And the x-coordinate is r cosine theta. And then we substitute the equation for r. And in this case, the equation for r is 4 minus 8 sine theta. The important thing to remember here is that we are actually going to leave this second sine theta right here. That's the same as this sine theta. And this second cosine theta right here, or this cosine theta, that's this cosine theta. So you can see kind of clearly that all we've really done is substitute for r. In this particular instance, I think it's a good idea if you distribute the sine theta and cosine theta in the numerator and denominator. Now the derivative of 4 sine theta is 4 cosine theta. And the derivative of 8 sine squared theta, well, that's a power rule. First we start with the 8. Then we multiply by the old power, which is 2. Then we decrease the power, so now we get sine theta, so 2 sine theta. And then we multiply by the derivative of sine theta, which happens to be cosine theta. Now the derivative of the denominator gets a little bit messy, so let's take a look at that. We have 4 multiplied by the derivative of cosine, which is negative sine theta. And then we have a product rule, so 8 times the derivative of sine, which is 8 cosine theta, multiplied by cosine theta. Now this negative sign in between the terms, that's just distributing the negative sign into the power rule, the product rule. Then we have 8 sine theta multiplied by the derivative of cosine theta, which is negative sine theta. Now since we're evaluating the derivative at theta equals 0, there's a lot of chances for a derivative to be equal to 0, or one of the trig functions to be equal to 0. In fact, every time I have a sine theta, I get to turn that into a 0. Let's see what that looks like. So we have dy dx equals to 4 cosine theta minus 8 times 2 multiplied by sine theta cosine theta divided by, well, that's just a big mess. First of all, whenever I see a cosine, I'm going to turn that into a 1. And then wherever I see a sine theta, I'm going to turn that into a 0. And that greatly simplifies things. We get 4 over negative 8, which is negative 1/2. Okay, we're off to a good start here. And let's take a look at question 2. So we have a particle moves in a plane so that its position at any time greater than 0 is given by x equals 5 secant of pi t and y is equal to 2 tangent of pi t. We're supposed to eliminate the parameter and find an equation for x and y, or in terms of x and y, for the path of the particle. Now I'm taking a look at this equation and it's kind of hard to see what to solve for here. And one trick that often gets used is to start off with one of those Pythagorean identities. What I mean is sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. And then 1 plus cotangent squared theta equals cosecant squared theta. And believe me, nothing is going to make you seem more like a trig god than if you memorize these 3 equations. And of course, if you're really good at using them. So looking at the work that we have, we've got x is 5 secant pi t and y is 2 tan pi t. So based on what I'm seeing is we don't want the first one or the third one. We want 1 plus tangent squared theta equals secant squared theta. We know that x equals 5 secant pi over t, which means x over 5 equals secant of pi t, and x squared over 25 is secant squared pi t. We're also given that y equals 2 tangent of pi t, which means y over 2 is tangent of pi t, and then y squared over 4 is tan squared pi t. Coming back to my Pythagorean identity, I've got 1 plus tangent squared theta equals secant squared theta, which means that 1 plus tangent squared pi t equals secant squared pi t. Tangent squared pi t, that's the same thing as y squared over 4. And then secant squared pi t is the same as x squared over 25. Now we're probably going to want to turn this into terms of, into a standard form. So this is equivalent to x squared over 25 minus y squared over 4 equals 1, which if I remember correctly, that is a hyperbola. So we're looking at a hyperbola here, or at least part of a hyperbola. Question 3, find all the points at which the tangent to the curve x equals 3 plus sine t, y equals negative 2 plus cosine t is vertical. Well, we get a vertical tangent line if dy dx is undefined, which means that if dy dx equals some constant over 0, we will have an undefined slope. Remembering in our parametric equations, dy dx is dy dt over dx dt. So the derivative of negative 2 plus cosine t over the derivative of 3 plus sine t, when is this equal to something over 0? Simplifying for our derivatives, the derivative of negative 2 is 0, and the derivative of cosine is negative sine. Looking at our denominator, the derivative of 3 is 0, and then the derivative of sine t is cosine t. We can simplify this to negative sine t over cosine t. So now the question becomes, when is cosine t equal to 0? And that happens whenever t is pi over 2, or 3 pi over 2, or 5 pi over 2. Basically any odd number multiplied by pi over 2. 2n plus 1 is your odd number generator if you were interested in that. So there we have it, number 3. Let's slide on down and take a look at number 4. Find the area of the region inside the circle root 3 sine theta and outside the cardioid 1 plus cosine theta. Here's our graph of root 3 sine theta. And then here's our cardioid 1 plus 1 cosine theta. I'm going to zoom into this so I can shade this in a way that's helpful to this problem. Now, whenever I shade polar functions, I always try to draw radii that are coming out from the origin. So something like this. Now, the region that we want is inside the circle, but outside the cardioid. So I'm going to go ahead, I'm going to keep drawing all of these radii. There's another one. And I'm going to keep drawing them. Here's another one. Until we get something that kind of looks like this. Now, if we want to be inside the radii, or inside the circle, but outside the cardioid, and basically, we're just talking about this region right here. And if you take a look at it, the radii do not go all the way to the origin, or basically I should say the region, the shaded region, doesn't go all the way to the origin. So this, to me, this looks like the area between two polar curves. The outside curve, which would be the very tips of the radii right here, that is the red curve, which is a circle. The inside curve is going to be the cardioid, and that's basically all these places where the radius ends and stops going through the region. That is at the cardioid. Okay. Now, the first radius is going to be at this intersection right here. So that's theta 1. And then the last radius, I don't know if you can tell as I was drawing them out, the last radius goes in this direction right here. And that's theta 2, which I know for sure that's equal to pi. So what is theta 1? That's our real first question. Well, the place where the two curves intersect is the place where the two radii are equal to each other. So in other words, for theta 1, we have root 3 theta 1 needs to be equal to 1 plus cosine of theta 1. Now, this isn't a very simple equation for you to solve. In fact, I would say that this is beyond what we need to do solving here. So we'll try some other methods here of solving. One of the first places I turn to is usually Desmos. You can see here that I've already graphed the two curves. And if I want to solve this, all I really need to do is type our equations. So the square root of 3 sine theta. Okay, that's equal to 1 plus cosine theta. And that is not going to do it for me. I think I need to change the variable to x. Oh, I made that a 2. That should be a 3. Let's make this an x and make this an x. And that is not solving it for me. Okay, so I was kind of being a little bit foolish here. We set the blue-purple equation is root 3 sine x, which is radius 1. The black equation here is 1 plus 1 cosine theta, which is the cardioid. And then to find the solution, we just find where the two y coordinates are equal to each other. And that's going to be at pi over 3. We can also look for the second point of intersection right over here. The next time they intersect is right here at theta equals pi. So with our 2 points of intersection and knowing which one is the outer radius and which one is the inner radius, we can get that the area is the integral from theta 1 to theta 2 of 1/2 r outside squared minus 1/2 of r inside squared. Let's substitute things in. We've got the area is integral from 0 to pi thirds of 1/2 root 3 sine theta squared minus 1 plus cosine theta squared d theta. I hope you don't mind that I factored out the 1/2. It's usually done. We could simplify this, or we can just go to a integral calculator to do that. I think I'm going to go and take the route of grabbing my TI and doing it from here. So let's find our integral. We're going to integrate from 0 to pi thirds. Put everything into our function. I also forgot to put the 1/2, so I put that at the very beginning. And we should be good to go. This gives us an area of, well, that's negative. Oh, silly me. I put the incorrect limits here. This should be from pi thirds to pi. All right, this should give us a good response. Yeah, 1.299. Now on an AP test, you wouldn't be expected to integrate anything but, the easiest of integrals. So I don't feel too bad integrating this. This looks like one of the kinds of integrals that you wouldn't be expected to integrate on an actual AP test. So this brings us to number 5, the last one we're going to do in this video. We want to find two sets of polar coordinates with rectangular coordinates 3, 3. We also want the radius to be positive, and we want our theta to be between 0 and 4. Now the first thing we're going to do is find our radius. Our radius is the square root of x squared plus y squared. Square root of 3 squared plus 3 squared. That's just the 3 square root of 2. Next thing I'm going to do is find our reference angle. Our reference angle is the inverse tangent of y over x, which is the inverse tangent of 1, which is pi over 4. Okay, this gives us our first coordinate in polar form, which is 3 root 2 as our radius, and pi over 4 as our angle. Now, we have to keep a positive radius here. Radius has to be greater than 0. And I'm realizing there's a little bit of a typo here, because this should be not 4, but 4 pi. So if we want to keep our radius positive, in order to get the next coordinate that maps there, we're just going to keep our same radius, like we said. But for the angle, we're just going to add 2 pi to pi over 4. Remembering that the angle of pi over 4 and pi over 4 plus 2 pi are exactly the same. Now, of course, you can simplify this. Instead of pi over 4 plus 2 pi, you can make that 9 pi over 4. But it's still the same angle. So that's it for questions 1 through 5. We'll see you next time when we tackle questions 6 through 10. Have a good one, everyone.